So welcome to Cafe Scientifique and welcome to my world of climate research. This evening, I want to give you some insights into how climate science works by focusing on the question, what do we know and how do we know it? You will be familiar with some of the things I will tell you, but I also hope that after this talk, you'll be able to say, I didn't know that, or better still, I understand that better now. Though the subject is global, a global one, I'm going to try and give it a local focus as well. All of us are bombarded with climate stories in the press or online, and it's often hard to know what to believe. The best outcome of this evening would be that I inspire you to find out more for yourselves, because there's growing evidence that climate change is a threat to our planet. Each of us plays a small role in causing the climate to change, and each of us can play a role in solving the problem. It's an enormous topic, so I'm going to have to be selective and will focus on 5 main topics. First of all, there'll be some basic facts about the Earth in the context of climate. Then we'll look at greenhouse gases and move on then to temperatures, followed by sea level rise and finally melting ice, before I make some general comments on climate prediction. We're going to start in the blackness of space before we see the Earth, 147 million kilometers from the sun, and seen here as it was from the Apollo 17 mission in December 1972. We're looking down on southern Africa, and most of what we can see is blue ocean. Not surprising, since the oceans cover 70% of the Earth's surface. White clouds mark out the weather systems, and in the south you can see the white Antarctic continent. We can even see some land. It's not surprising that pictures like these are often referred to as blue marble images. Such images are thought to have been a catalyst to start the environmental movement, highlighting as they do the fragility of Earth. They also led Arthur C. Clarke, best remembered nowadays for 2001: A Space Odyssey, to say that our planet ought to be called Ocean, not Earth. I've now added a blue ring, a thin blue ring, to indicate the atmosphere, all that separates us from the cold of space. To an astronaut on the International Space Station, the atmosphere is clearly visible. It's very thin. The troposphere, the lowest layer, contains 80% of its mass, gases, mostly nitrogen and oxygen and water vapor. On average, it's 13 kilometers thick, thickest near the equator, thinnest near the poles. To show how thin, just imagine the Earth as the size of a soccer ball. The troposphere would be the thickness of just a couple of sheets of paper. Now we'll look at the fundamentals of what keeps Earth as at a habitable temperature. Here we are, orbiting the sun and bathed in its light. Bright light centered on the visible part of the spectrum, but with significant shorter wave ultraviolet, from which we are fortunately protected by the ozone layer high in the atmosphere. The energy received by the Earth at the top of the atmosphere averages about 1.3 kilometers for each square meter. The incoming radiation is reflected, absorbed and filtered by clouds and radiated back out to space, mostly as infrared radiation. So if the amount of energy radiated back to space equals the amount received from the sun, then the temperature of the Earth will stay at the global average of about 14 degrees Celsius. Changing that balance by even a small amount leads to either warming or cooling. The processes that go on within and below that thin layer of atmosphere and that govern the radiation balance are very complex. We call it the climate system. Here's a very simplified cartoon. We see land and oceans, rivers, lakes, clouds, rain, snow, vegetation, and all the major processes, things that have been around for thousands, indeed millions of years. But we now have human influences, you and me, damming rivers, changing land use, driving cars, heating our homes, flying, remember that? And most importantly, using fossil fuels, oil, gas, and coal that have been locked away beneath the ground for millions of years and that we have been burning since the start of the Industrial Revolution just 250 years ago, producing about 100 million tons of CO2 each year and releasing it into the atmosphere, where it joins all the other gases, whether naturally occurring or man-made. So let's now move on to the focus of my talk. What do we know and how do we know it? I first want to introduce you to some pioneers who helped us understand the consequences of our influencing the climate system. We'll start with the Frenchman, Joseph Fourier, best known as a mathematician, but in 1825, he worked out that the Earth was warmer than it should be based on its distance from the sun, and speculated that the atmosphere might be the cause. 30 years later, in America, Eunice Foote filled sealed jars with various gases, including carbon dioxide, and found that in sunlight, they warmed by different amounts. Next came Englishman John Tyndall in 1859, who measured how much infrared radiation was absorbed by carbon dioxide and by water vapor. And finally, the Swedish scientist Svante Arrhenius, who in 1889 estimated that doubling the amount of CO2 in the atmosphere would raise Earth's temperature by about 4 degrees Celsius. It turns out that that was a pretty good estimate. So the evidence has been around from very early on that carbon dioxide plays a role in warming the Earth. Though tonight we are just going to focus on carbon dioxide, there are many other gases that contribute to global warming, and many have a much greater potential than CO2 to affect climate. Methane, for instance, is about 30 times more effective. So how do we know how much carbon dioxide is in the atmosphere? Well, here's the man who was instrumental in telling us. He's an American, Charles David, known as Dave Keeling. In the late 1950s, he had a new PhD in geology, but had also developed a method to accurately measure the carbon dioxide in air samples. He was hired to work as a researcher at the Scripps Institution of Oceanology, just north of San Diego in California. If you have to work as a researcher at the Scripps Institute, if you have to work anywhere, this is certainly the place to be, an ideal spot. I can vouch for that. At Scripps Institution, he joined Roger Revelle, who was beginning to take an interest in CO2 in the oceans, and they started to collaborate. They made an odd couple, Keeling rather slight, as you've seen, Revelle around 6'4" and with enormous feet. Dave Keeling started to make systematic measurements of CO2, firstly at Scripps, but later at the Mauna Loa Observatory on Hawaii, in the pristine air at a height of 10,000 meters. It didn't take long to show that CO2 levels were increasing. Revelle, by then the institution's director, helped Keeling overcome times when the agencies who were funding the measurements said, "You've been measuring this for 10 years. Why do you need to continue?" And so the Mauna Loa measurements continue to this day. Here is the curve, known as the Keeling Curve, starting at under 320 parts per million by volume in 1960 and rising year on year and now standing at 415. There is detail in the measurements throughout each year, reaching a maximum in May and a minimum in October, reflecting the seasonal cycle of photosynthesis and the fact that there is more land in the northern hemisphere than in the southern. Since the 1980s, we have established a worldwide network of air sampling stations under the auspices of the United Nations Global Atmosphere Watch. Sites are on continents and islands, the red dots, and there are measurements from ships. And 3 reference stations, Mauna Loa, naturally, Alert in northern Canada, and Cape Grim in Tasmania, measuring a wide range of gases and pollutants. But what were the levels of CO2 before Keeling started, and what might they be in the future? The answer to the second question is in all our hands. To answer the former, we really need to analyse some pre-1960s air. And where could we find that? I'm going to have to take you to the ends of the Earth, to Antarctica and to Greenland, where snow builds up each year as it falls, but doesn't completely melt. It builds up in annual layers, and scientists have drilled down through that compacted snow and ice, and trapped in those layers of ice are tiny bubbles, each containing air from the year in which the snow fell. Those ice caps are over 3 kilometers thick in Greenland and almost 5 kilometers in Antarctica. By cleverly measuring the gases in the trapped bubbles and determining their ages, a method too complicated for this talk, we can find out what happened in the past. First, over the last 2,000 years, we see a record made by combining ice core data with the Cape Grim samples. It shows that the trend in the Keeling curve extended back to the late 19th century, soon after the start of the Industrial Revolution. And going much further back in time, in fact, 800,000 years, we can see that over that time, values stayed between 190 and 300 parts per million. Very different from where we are today at 415. And now for something completely different. A photograph of a family taken in 1911 in their garden in Hull and wearing their best hats. But it's not the hats that we're interested in, but the mysterious white slatted box on stilts. A beehive? A bird cage? No, it's called a Stevenson screen, and it would have contained thermometers from which the garden's owner made careful temperature measurements. The thermometers, well ventilated, at a standard height between 4 and 6 feet above the ground, and screened from direct sunlight. This little insight into Britain's fixation on weather records leads us nicely into a local question. Is Southampton getting warmer? In Southampton, careful standardised measurements made by the Met Office, then a branch of the Board of Trade, started in 1850 and continued in Mayflower Park until the year 2000, when the measurements ended. The observations, which are available from the Met Office website, show the average temperature calculated for each year and seem to show a rising trend. But of course, we wish the record had continued. So how can we extend it? Well, in 1960, the Met Office started a similar station at Herne, now Bournemouth Airport, 20 miles to the west, and that continues to this day. The red line is that record. Fortunately, the two records overlap and the year-to-year variations match very closely. We can see that Bournemouth Airport is a bit colder than Southampton, further from the sea, more rural location, different soil or vegetation. But because the two records overlap and so are similar, we can adjust Bournemouth to align with Southampton and combine the two. And now we have a record that it makes the changes clearer and suggests that Southampton is now 1.5 degrees warmer than it was 150 years ago. But just as we did with the CO2 records, we should ask, how does that relatively short series from Southampton and Bournemouth fit into the bigger picture? And just, is this obscure? Is that better? Yeah. Right. The clue is as to how to start lies in that photograph with the hats. The UK has had many enthusiastic amateur meteorologists whose records stretch back to the 18th century. Many were country landowners and clergymen who kept detailed diaries and recorded the weather. The key person who carefully compiled and analysed these early records, together with records from observatories, was Professor Gordon Manley. He first published what is now known as the Central England Temperature Record in 1953. It is a record that roughly represents temperatures in a triangle between in an area between London, Lancashire and Bristol, and has since been extended with more modern Met Office records. And here is that record, showing month-by-month departures of average temperatures from the mean value. There are the inevitable ups and downs, but it also shows a few persistent cool periods in the early 1800s and around 1880. It turns out that these follow closely after major volcanic eruptions in what is now Indonesia, Tambora and Krakatoa. And there's even a hint of the influence of the eruption of Laki in Iceland in 1783, reported in the records of Gilbert White at Selborne. But can we delve even further back? Where are temperatures recorded from thousands of years ago? Surprisingly, we can get them from the ice cores I talked about earlier. It's a bit of a complicated method. The snow that falls is made from water evaporated from the oceans. Though water, H2O, is made up of 2 hydrogen and 1 oxygen atom, those atoms can exist as heavier isotopes, oxygen-18 and deuterium. The water molecules made from these heavier isotopes take a little bit more energy to evaporate than standard H2O. This means that the warm years produce snow with more of the heavier isotopes and the cold years with less of them. By careful analysis, the temperature changes can be deduced. And here is the record. You may think there is some similarity between this record and the CO2 record I showed earlier. You are not deceived. The changes in temperature and CO2 move together as Earth switches between cold ice ages and warmer interglacial periods, such as the one we're in now. Comparison of these graphs implies that changes of about 70 parts per million in CO2 resulted in changes of about 9 degrees in Earth's temperature. CO2 levels are now 140 parts per million above pre-industrial levels. I want to introduce you now to the complex modern international network of climate observations. Here is a schematic showing measurements from land stations, ships, aircraft, and from satellites, feeding their data into weather and climate centers. In fact, Earth observing satellites now play an essential role, but are relatively new. Most of the satellite records only started in the 1980s. However, they have huge advantages. They can work in all weathers, their cover is virtually global, and they are blind to national boundaries. Satellites, however, have vulnerabilities and present challenges. They take many years to plan and build. Everything is dependent on a successful launch. They are expensive, often running into billions of dollars, so costs often have to be shared. And many variables are not measured directly, so you still require traditional ground truth measurements to keep them honest. Another important factor not explicitly shown in this schematic is that merging all those various data streams requires sophisticated computer models. The global all-weather coverage from satellites does give remarkable insights, and I will show you three of these. The first is patterns of global temperature change. Here is the monthly temperature anomalies starting around 1980. There will be lots to focus on, but first note that the biggest warming events, the pink areas, are mostly at high latitudes. We'll start to run this. Secondly, there are patterns of variability that show up, mostly noticeably when there are El Nino events. That's when the warm water normally found in the western equatorial Pacific makes an excursion into the normally cool eastern Pacific and disrupts weather patterns worldwide. You'll see these events around 1982, 1997, and in 2014. At the bottom, you can see a graph building up showing the global average temperature. I'll just leave this to run now and point out things as they occur. Again, you see the large amounts of warming, particularly over northern Russia and Siberia. You'll see an El Nino event coming up fairly soon in the Pacific. If you look over here, here it comes, and then sloshes back westwards again. And so we reach the end of the record in 2019. Strong warming over the Bering Straits here and over northern Russia. Perhaps the most concerning is the fact that by the end, virtually all of the Earth is warmer than the 1981 to 2020 average. And again, with the greatest change at high latitudes, where melting of the permafrost has the potential to release lots of methane into the atmosphere. We haven't yet said much about measuring the oceans, and that's going to be the focus of the rest of my talk. First, some facts. I've already mentioned that they cover 71% of the Earth's surface. On average, they're about 4.8 kilometers deep, and they hold 96.5% of Earth's water. The remainder, 1.7%, is in lakes and rivers and 1.7% in groundwater, leaving a very small proportion in the atmosphere and able to form as life-sustaining rain. Water, and hence the oceans in particular, have a very high heat capacity to store heat and hence for ocean currents to move that heat around the globe. And finally, the oceans are opaque to light and to radio waves. This poses a problem for oceanographers and also means that satellites basically only see the ocean surface. Historically, to make measurements beneath the ocean surface, you had to lower temperature instruments on long wires from research ships. And here are some of the ways we used to and still do observe the oceans. So starting in 1870, lowering thermometers on wires from ships. And then from the 1970s, we had instruments which continuously recorded temperatures from the surface to the bottom of the ocean, but still had to be lowered from ships. And then from the 1980s onwards, we had satellites, we had much better communication, and so we could have buoys relaying data back from the oceans. So what progress have we made? Well, here is a map showing all the measurements that have made down to a depth of at least 2,000 meters in the ocean between 1870 and 2018. They're color coded, the dense areas are red, the sparse areas are blue, and the areas with no observations are white. You can see that the measurements are heavily biased towards the northern hemisphere, and large areas in the southern hemisphere are without observations at all. So that's 500,000 observations covering an area of the oceans of 360 million square kilometers. That's very few. Since the year 2000, we have had an array of 4,000 profiling floats, drifting with the currents below the surface, each float surfacing every 10 days, recording its data of temperature and salinity and relaying it back to satellites. These are operated by 30 countries, and the data are shared freely between those countries and in fact all countries. And those data now provide us with a completely uniform cover. And this is again the number of observations, but we now, including the profiling floats, there are now 2.3 million observations. And you can see the coverage is uniform over virtually all of the oceans, apart from around Antarctica, where there are ice-covered areas, which make such observations difficult. We can use observations like that to calculate how much heat is stored in the ocean. And here are the results published just 3 weeks ago by a team of 23 Chinese, American, and European researchers. The curve is like many of the others we've seen this evening, showing the big changes starting around 1980. The numbers are enormous. The amount of heat gained by the ocean just in the past year, just that little bit there, is the equivalent of every person on the planet having 12 hair dryers and running them continuously for 365 days a year. The oceans are vital for Earth's climate. They mop up about 92% of the heat gained by the Earth through greenhouse gas warming. That slight imbalance between incoming and outgoing radiation. And one consequence is sea level rise. Of course, we've been unwittingly measuring sea level rise for at least a couple of 100 years, because mariners have needed to know about tides and have made systematic measurements and referenced them to benchmarks, such as the one in Newlyn, to which the Ordnance Survey maps are referenced, and this one at Port Arthur in Tasmania, set up in 1830. Of course, we now have more modern methods using satellites bouncing radar from the ocean surface. They are precisely positioned by GPS, the subject of our next Café Scientifique talk, and since the 1990s have measured sea level globally to millimeter accuracy. There are some fascinating, eye-catching videos of changes in the shape of the ocean surface, but in the interest of time, I'm just going to summarize the results into one picture. It shows both the recent satellite altimeter data, the red curve on the right, and the earlier tide gauge measurements. You'll see that the newer data have much less uncertainty than the old sparse data. From this picture, we can deduce that since the 1880s, the globally averaged sea level has risen by about 22 centimeters, 8 or 9 inches. About half due to the oceans warming and expanding, the remainder due to the melting of the polar ice caps and alpine glaciers. The damming of rivers has had a small effect of slowing the rise. We can also see the effect of volcanic eruptions. But unfortunately, all of the major ones occurred before we had a satellite altimetry and before we have Argo. We would love one now. It would be a wonderful experiment to see the effects of a major volcanic eruption on the satellite measured sea level and on the data from the Argo array. The rate of rise is accelerating and is presently about 4 millimeters per year. And if we continue to emit CO2 at the present rate, called the business as usual scenario, sea level will be between 40 and 80 centimeters higher by the year 2100. A sobering thought when you consider that 600 million people worldwide presently live less than 10 meters above the present sea level. Lastly, we're going to look at disappearing Arctic sea ice. This is not the ice in Greenland and the Antarctic ice caps that we talked about earlier, the melting of which will contribute to sea level rise. No, this is the frozen seawater that fills the Arctic Ocean. These data are from satellites that can show where the ice is, how abundant it is, how thick it is, and how old it is. We are looking north from high above Canada towards Siberia. The interesting things happen both in the Arctic and also in the gap between Greenland and the UK on the right. We'll run it and I'll point things out as we go. We start in 1984 and finish in 2019. Multi-year white ice lies mostly north of Canada. Each year we see ice-free areas open up along the coast of Siberia. And the ice leaves the Arctic through the Denmark Strait between Greenland and Iceland in a steady stream, mostly in the winter. In the Labrador Sea, west of Greenland, you only see annual ice. You never see the white multi-year ice. The monitor on the top left, the white bar, shows how much multi-year ice there is. Here we're in 1997, and there are about just under 2 million square kilometers of multi-year ice. I'll just leave this video to speak for itself and then make some comments about it at the end. That's another 10 years to go, but look how there's almost no multi-year ice in that monitor on the left now. almost at the end. And there we are. If you ever thought the Earth had a pulse, I think that video might be cited as evidence. But through that annual pulsing, you probably detected that there is much less ice around now than there was in the 1980s. You'd be right. Here's the minimum in September 1984, the September summer, and here it is in 2019. I'll switch back and forward between those, and you can see the huge changes that have gone in the Arctic Ocean. The difference is striking. Since 1984, sea ice extent has declined by about 13% each decade. Hence the speculation as to when the Arctic might be completely ice-free, or at least provide a year-round trans-Arctic shipping route. The decrease is caused both by melting at the upper surface of the ice due to higher air temperatures, and also due to warm water from the Atlantic melting the underside of the ice. Of course, we'd love to have records stretching further back, and we can do something to learn about that by looking at the logbooks of ships that plied the Arctic and its fringes, hunting seals and whales. And here's a reconstruction of where the maximum and minimum were during the 19th century. You can see that in both show ice around Iceland, something not seen nowadays. We've looked into the past, so let's look into the future. The saying of the nuclear physicist Niels Bohr, prediction is very difficult, especially when it's about the future, certainly holds good. Making those predictions of the future of Earth's climate depends on knowing the past, on continuing to measure, on maintaining high standards of measurement, on understanding how the climate system works, and on using models. If they can reconstruct the past, then they may have skill to predict the future. Perhaps the greatest uncertainty lies in understanding how we humans will behave in the future. We will learn more this coming year because of two big events and many other smaller steps. In this coming year, the Intergovernmental Panel on Climate Change, the IPCC, will issue its sixth assessment of the global series that started in 1990. This is a summation of all we know about climate and is signed off by every country in the world. And then in November in Glasgow, the Conference of the Parties of the Framework Convention on Global Climate Change, COP26, will try to agree on what governments could do about greenhouse gas emissions. And through the year, there will be new climate headlines, but best of all, there will be new scientific discoveries. I hope that I've given you some new insights into the world of changing climate, and particularly into the wide variety of observations and measurements on which our understanding is based. Measurements by professionals, on land, on sea, at the poles, and from space. Measurements by amateurs, and measurements used for purposes for which they were not originally intended, or have value as pieces of the climate jigsaw. This has been a very brief summary, and there are many topics that would warrant a dedicated talk. But I want to end on an optimistic note. Here in the Northern Hemisphere, spring is on its way. Soon we will see cherry blossom. In Japan, of course, the cherry blossom flowering marks a major annual festival and has done for hundreds of years. But on what date will the blossoms reach their peak? Well, Here are the dates recorded back to the year 800. Now, blossom peaks in early May, in early April. Previously, it peaked around the mid-April. And so we've seen change, another measure of our changing climate. Here's to spring. Thank you.